Welcome back on my today's session on static and time varying field and some important questions on static and time varying field. Myself, Dr. Sayanti Chatterjee, Associate Professor of Electrical and Electronics Engineering in IARE, Hyderabad. So, the main course, first we will discuss how time varying fields are developed. So, time varying field means it is continuously changing with time. It is continuously changing with time. You can see one is the green one. Green one is the electric field. The green one is the electric field and the blue one is the magnetic field. When the electric field superimposed on the magnetic field, a time varying field has been generated. So, time varying fields are produced due to the accelerated charges or time varying current. If the currents are changing its direction, time varying current, then the time varying charge will come. Next one is a time varying electric field is produced by a time varying magnetic field, and a time varying magnetic field is produced by a time varying electric field. So what is this? A time varying electric field is always produced by a time varying magnetic field. If magnetic field is continuously changing, the electric field will change, and that if the magnetic field is changing, the electric field will also change. The first concept was first experimentally introduced by the Michael Faraday, and then theoretically it was proved by the James Clerk Maxwell. That's why Michael Faraday and James Clerk Maxwell are known as the father of the electrical engineering. Next, we will discuss about the Faraday's law. So, Faraday's law is the basics of the electrical engineering. Faraday's law has the three parts. First part is any change in magnetic field of a coil of wire will cause an EMF to induced in it. The EMF induced is called the induced EMF. And if the conductor circuit is closed, the current will always circulate through the circuit. And this current is known as the induced current. What are the methods for changing the magnetic field? How we can change the magnetic field? Number one method is by moving the magnets towards away and from the conductor. If we move the magnet continuously, the flux density will change, and it will cause the rate of change of flux. Number two, by moving the coil into or out of a magnetic field. If there is a new north pole and south pole, this is the coil. If we take the electrical coil also we change the position of the electrical coil, then also it will creates a rate of change of flux. By changing the area of a coil placed in the magnetic flux, like the piezoelectric material, if we change the volume or the area, and that will change the magnetic field. By rotating the coil relative to the magnet. So this is the main working principle of a generator. If we rotate the field continuously, what will happen? It will create some field. So if by rotating the coil relative to the magnet, it will create the rate of change of field, and it will cause the induced EMF. Next, we will discuss about these are the four important topics. What is Faraday's second law? It states that the magnitude of the EMF induced in the coil is equal to the rate of change of flux that linkage with the coil. The flux linkage of the coil is the product of number of turns in the coil and flux associated with the coil. So it states that the magnitude of the EMF induced in the coil is equal to the rate of change of flux that linkage with the coil. The flux linkage of the coil is the product of number of turns in the coil and flux associated with the coil. So from the Faraday's law, we can write that the E is equal to minus d phi by dt. E is equal to minus d phi by dt. And this minus comes from the Lenz's law. What is the Lenz law tells? Lenz law tells the direction of the induced EMF will be such that it will oppose its cause. It will oppose its cause. That's why E is equal to minus d phi by dt and E is equal to minus n d phi by dt. E is equal to minus n d phi by dt. Explain the force on a moving charge. So what is the force on a moving charge? When magnetic fields can exert a force on the electric charge only if it is moving. If it is a electric charge is fixed, it will not give any force. Just as a moving charge produces a magnetic field. Just as the moving charge produces a magnetic field. This force increases with both an increase in charge and magnetic field strength. The force increases with the both if the charge amount is increased and magnetic field is increased, the force will increase. Moreover, the force is greater when the charges have the higher velocities. Because if charges is the higher velocities, the current will be more and the force will be more. And the force, however, always acts perpendicular to the velocity. The direction of the force is always perpendicular of the velocity, and we can write force is equal to Q V cross B. Q V cross B, where Q is the charge, V is the velocity, and B is the magnetic field or magnetic flux density. Thus, it always acts out of the plane and does not contribute to any work done on the charge. It is always perpendicular, and we know force is equal, work done is equal to Fs cos theta. As it is perpendicular to the velocity, then we can write that thus it doesn't contribute to any work on the charge. It can merely change the direction of the velocity but cannot change its magnitude. The direction of force can easily be determined by the Fleming's right-hand rule. The direction of the force, if Q and V cross B in this direction, we can get the direction of the force from the Fleming's right-hand rule. If we take our three right hand fingers perpendicular to each other, if the middle finger gives the direction of B and the thumb gives the direction of velocity, then F will give the direction of the force. So this is the procedure of the force on a moving charge. Depend on F is equal to Q V cross B. But this is only when the moving charge is in the magnetic field. Explain Lorentz force. What is Lorentz force? So when an some electrical charge or current is flowing through a magnetic field, it will experience an electric force, and electric force Fe is equal to Q into E. Fe is equal to Q into E. Again, we know the Fm is equal to, just we discussed, when the electric charge moving to the magnetic field, we can write Fm is equal to Q V cross B. V cross B means velocity cross the electric field strength. So what is the total force experienced by the charge? Electric field plus magnetic field. QE plus QV cross B, or we can write QE plus V cross B, and this is known as the Lorentz force. This is known as the Lorentz force. So Lorentz force has two parts. Q is the electric charge, E is the electric field intensity, V cross B means velocity cross the B. B is the flux density. What are the limitations of the moving charge in the magnetic field? The limitations of moving charge in the existing magnetic field. 1. If the velocity of the charge in the magnetic field is 0, the force experienced by is 0. If V is 0, the force is 0. If the velocity direction and magnetic field directions are parallel to each other, then force experienced is 0. As I told, V cross B, as we know, E is equal to V cross B. So if the velocity and the magnetic field is equal to 0, V cross B means VB sin theta. So if the velocity is parallel to the flux intensity, the theta is equal to 0, and the force will be 0. To say that moving charge in the magnetic field experiences force when velocity and field must be normal to each other. When they are normals, means theta is equal to 90 degree, then the moving charge will feel the maximum amount of force. Deduce the force on the current element due to the magnetic field. So this is a current element. We got dF is equal to dq V cross B. Already these questions I have discussed in the magnetostatics also. Just it is a repeating answer, but we have to check. dF is equal to dq V cross B. What is B? B is the dl by dt. If the conductor length is dl, then we can write dq is equal to dl cross B. Again, we know what is dq. dq is equal to rho v into dv. What is dq? dq is equal to rho v into dv. So df we can write process 1, the second part. Next we can write it as rho v dv v cross B. This is the another expression of the force from the on the moving charge. Again, we know dv is nothing but the volume. We know dv is nothing but the volume. So we can write it as the J cross B into dv. How we can get this? We know rho v into dv is equal to J. We know rho v into dv equals to J. So J cross B dv. Again we can change it. What is dv? dv is equal to volume into length, and J is equal to I into ds. So we can also write as I cross B dl. I cross B dl, and also we can write it VIL sin theta. So force on a current conductor can be written in a different format. In details I have discussed in my previous lecture also. This is one quick revision, that the force is equal to VIL sin theta. F is equal to VIL sin theta. Write the expression of the force due to a parallel straight conductor. Let us assume there are two parallel straight conductors P and Q, and the distance between them is D. So the H is equal to I1 by 2 pi D. H for the current I1 from the Ampere circuital law, we got intensity H is equal to I1 2 pi D. So what is the flux density? Mu naught I1 by 2 pi D. Just we discussed for force on the I2 due to I1. Force on the I2 due to I1 is equal to BIL. We are taking it sin theta 90 degree maximum. So F is equal to BIL. So B value we got mu naught I1 by 2 pi D. I2 is the current. So we can write B is equal to mu naught I1 I2. B is equal to mu naught I1 I2 by 2 pi D. Sorry, this is the force is equal to. So what is the force per unit length? Force per unit length is mu naught I1 I2 by 2 pi D. Similarly, we can also get the F2. the force on the first conductor due to the current I2 is equal to mu naught I1 I2 by 2 pi d. So this is the long force for a long current carrying conductor. Then state the Lenz law. What is Lenz law? Lenz law tells that the cause opposes every cause of producing it. What is this say? This is a north pole and south pole. We are moving one current carrying conductor here, and what is the thing? It will create some flux, and the direction of the flux will be oppose its cause. So directions of the induced EMF drives the direction of the induced EMF drives the current around a loop to always oppose the change in magnetic flux that causes the EMF. Then write the Maxwell's fourth equation. We know from the Gauss law flux phi is equal to integration of Bs ds. And we also got from the Faraday's law E is equal to minus d phi by dt. We got from the Faraday's law E is equal to minus d phi by dt. So in the place of phi, we can write integration of B ds, surface integration of B ds. So E is equal to d by dt integration of B ds. Again from the what is the electric potential? E is equal to my E integration of E dl, and for a open circuit is known as the EMF, and a closed circuit it is known as the electric potential. Both are same. It is in the open circuit, this is in the closed path. So V is equal to V equivalent to E is equal to integration of E dl. So integration of E dl is equal to minus surface integral of dV ds by dt. So this is the Maxwell's equation in an integral form. This is the Maxwell's equation in the integral form. So now we are using the Stokes theorem because this is dl and this is ds. So we can write in the place of E, we can write it in the grad cross E ds from line to surface integral. As this is a vector quantity, we will use the Stokes theorem, grad cross E ds. So grad cross E ds is equal to integration of dB ds by dt. So if both side is ds, so we can write grad cross E is equal to dB by dt, and it can also written by grad cross E is equal to del B by del T, because B is a three-dimensional thing. As B is a three-dimensional thing, so we can write grad cross E is equal to minus del B by del T. So these equations is known as the vector form of Maxwell's fourth equation, or vector form of Faraday's law, or Maxwell's equation in the point form. This is the Maxwell's equation. Maxwell's equation in integral form, and this is the Maxwell's equation in point form. So these are the two Maxwell's equations. Next one is the state the Gauss law. What is Gauss law? Electric flux passing through any closed surface is equal to the total charge enclosed by the surface. What is Gauss law tells? The number of electric flux passing through any closed surface is equals to the total number of charge enclosed. Gauss law psi is equal to psi is the electric flux, ds is equal to the flux density. Flux density in the direction of ds is equal to charge enclosed into the Q. If we think this is a surface and number of charge is equal to Q, the direction of the flux density is ds and s is the s, then we can tell that the Q, number of charge enclosed, is equal to the number of psi. The unit of psi is also coulombs. This is the Gauss law. Next is the name the types of EMF induced in the coil. According to the Faraday's law, whenever there is a change of flux, there is some induced EMF. So induced EMF can be written as we are getting the induced EMF from the Faraday's law. Induced EMF E is equal to minus d phi by dt. What is induced EMF E? Induced EMF E is equal to minus d phi by dt. Induced EMF can be divided into two parts. One is the statically induced EMF, another one is the dynamically induced EMF. What is statically induced EMF? In the statically induced EMF, conductors are stationary and flux is variable. In the conductors are stationary, means conductors are fixed and flux are changing. We can get the statically induced EMF, we can tell it as the, and what is the dynamically? Conductors are rotating and flux is constant. So this is the example of generator. Generator is an example of the dynamically induced EMF where conductors are rotating and the flux is fixed. What is the example of statically induced EMF? The induced EMF is the transformer. In the transformer, what happened? The flux are moving but the conductors are stationary. Define the dynamically induced EMF. What is dynamically induced EMF? In order to generate a dynamically induced EMF, the magnetic field system must be kept stationary when the, this is the statically, question is wrong. This is the statically induced EMF. This is the definition of the statically induced EMF. So what is statically induced EMF? What is statically induced EMF? The magnetic field system must be kept stationary when the flux is moving. If the conductor cuts across the magnetic field, the EMF is induced in the coil. Induced in the coil, and we can write E is equal to BVL sin theta. Example is motor. What is statically induced EMF? In order to generate a statically induced EMF, the field must be stationary and conductors are stationary. So in this method, conductors cuts the field and EMF will induce the. So what is the maximum value of the statically induced EMF? We know in the case of the statically induced EMF, the flux is moving. So E is equal to minus N d phi by dt. Now as this is a time varying field, we are assuming the field is also time varying. As this is a time varying field, we are assuming the field is time varying. So phi is equal to phi m sin omega t. Then the EMF induced is equal to N d by dt phi m sin omega t, N phi m omega cos omega t. When omega t is equal to 0, we will get the maximum value. What is conductor current density? Conduction current density refers to the amount of charge flowing on the surface of a conductor in a time t. So when current is flowing, the total current has two parts: current flowing through a resistor and current flowing through the capacitor. IR is known as the resistive current, current through the resistance or conductive current, and IC is known as the capacitive current. IR is the current through the resistance, IC is the current through the capacitance. Current through the resistance and current through the capacitance. You can see this is the IR and this is IC. IR is the conduction current, current flowing through the on the conductors on the conduction band. Next, we can write, if we divide the equation I by A is equal to IR by A plus IC by A. IR by A is equal to, so I by A is equal to J is equal to JR plus JC. JR is known as the, what is JR? JR is known as the resistive current density. Write the integral form of Faraday's EMF equation, or we can write it as the modified Maxwell's equation. We know grad cross H is equal to J plus D by dt. Grad cross H is equal to J plus D by dt. D by dt is nothing but the JC. When current flows through an coil, there is some leakage current or displacement current is always present, and the equation of the displacement current is d by dt. What is J? J is the conduction current, so sigma E, and d by dt, if as flux is time varying, so d will be time varying, and the maximum value will come as the g omega d naught. So J sigma E is equal to, what is d naught? D naught is equal to, D naught is equal to sigma epsilon into E. So if we take the E constant, J omega E. So HDL is equal to sigma J omega E integration of E ds is the modified equations of the EMF. Next is the self-inductance. What is self-inductance? Self-inductance is the property of the current carrying conductor that resists or opposes the change in current flowing through it. This occurs mainly due to the self-induced EMF produced in the coil itself. This occurs mainly due to the self-induced EMF. When flux is flowing through it, there is a cut of flux and it will induce the EMF in it. In essence, the direction of the induced EMF is always opposite to the applied voltage. If the current is increasing in the direction, the induced EMF will be in the same direction as the applied voltage. If the current is falling, if the current is increasing, then it both are in the opposite direction. If current is falling, they are in the same direction. The unit is Henry. The unit of the self-inductance is Henry. And induced current always opposes the change in current in the circuit, whether the change in the current is increase or decrease. Self-inductance is an example of the electromagnetic induction. Whatever we have discussed about the Faraday's law, self-inductance is the application of this. Then in the opposite side it comes, what is a mutual inductance? When two coils are brought in proximity with each other in the magnetic field, in one of the coils tends to link with other, and this further leads to a generation of the voltage in the second coil. This property of the coil, which affects the change of the current and voltage in a secondary coil, is known as the mutual inductance. So if two coils are in the proximities nearer to each other, the flux from one will change to the other. So if we draw it, if this is a coil and this is a coil, if we flow some current, the flux will generate phi 1, 2, and this flux will link the second one, and it will create some inductance in this, and this is known as the mutual inductance. So you can see, this is one N1, N2, this is the coil 1, this is the coil 2. So this, where current is flowing, this current I1 is flowing from here, it will create some flux, and this flux will also links the second coil. So we can write N2 phi 2 is directly proportional to I1. So N2 phi 2 is equal to M21 I1. Similarly, N1 is directly proportional to N1 phi 1 is directly proportional to I1, and N1 phi 1 is equal to M1 to I2. So if both are equal, we can write from the Ampere circuit law, mutual inductance M12 is equal to M21. What are the series connection of the inductor? If two inductors are connected in the same series added, if they are series added in nature, we can write L equals to L1 plus L2 plus 2M. If they are in the opposing nature, series opposing nature, we can write L is equal to L1 plus L2 minus 2M. You can think here current and current both are in the same direction. So we can write if it is L1, AN and SN, it is L2. So L1 plus L2 plus 2M, because one is actually L1 plus M12 plus L2 plus M21. But as M12 and M21 both are equal, so we are writing L1 plus L2 plus 2M. Similarly, L1 plus L2 minus 2M. This is the series and parallel connection of the conductor. If it is series parallel adding conductor, then we can write L is equal to L1 L2 minus M square by L1 plus L2 minus 2M. If they are the parallel opposing conductor, parallel opposing, series we have discussed, if they are parallel opposing, then L1 L2 minus M square by L1 L2 plus 2M. This dot sign means the current directions are same. This sign means the current directions are opposing. The M is in opposite direction. When they are in opposing, it is plus 2M. When they are in the same direction, it is minus 2M. Newton's formula already I have discussed. Energy stored in a conductor. Work done is equal to the energy stored. When current flows through an inductor, there is a rate of change of current, and dW is equal to VI dt. Actually, power is the V into I, the instantaneous power. So what is V? V is equal to L di by dt into I into dt. So we can write it like dW is equal to Li di. So integration of Li di is equal to Li square by 2. So this is my today's discussion, some important topic on the electromagnetic field and the time varying field, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.